Welcome back, students. Today we will start new topic, Rolle's theorem from applications of derivatives. So let us begin our topic, the Rolle's theorem or the Rolle's lemma. What is the statement of a Rolle's theorem or Rolle's lemma? If a real valued function f is continuous on closed interval ab, differentiable on the open interval ab, and f of a is equal to f of b, then there exists at least one point c in the open interval ab such that f dash at c is equal to 0. This is the Rolle's theorem. Now there are uh, three conditions in this Rolle's theorem. What are those conditions? The given function is a real valued function must be continuous on closed interval. This is the first condition. What is the second condition? The function is differentiable on the open interval. This is the second condition. And the third condition is the value of the function at the end points must be same. If these three conditions are satisfied, then we say that the Rolle's theorem is satisfied for the given function and there exists a point C in this open interval AB. There exists a point C in this open interval AB such that derivative of the function at that point C is equal to 0. What does it mean by that? It states that the real value, the differentiable function that attains equal values at two distinct points on it must have at least one stationary point. What it says? It has at least one stationary point somewhere in between them. Stationary means it's the first those points at which the first derivative becomes 0 are called stationary points. The point where the first derivative becomes 0. Okay, now we already see that finding the derivative of the function at particular point means we are finding the slope of the tangent to that curve at given point. That means we are saying that there exists a tangent which is parallel to x-axis, doesn't it? So these are the functions. F of x is the real valued function defined on the closed interval ab, and it is continuous on the open interval ab. This means that we have to draw the graph of f of x between x is equal to a and x is equal to b. This is the function f of x. This is the graph of the function. And if f of a is equal to f of b, the function at x is equal to a and at x is equal to b, function is having the same value. Function is having same value. Okay, same value at both the points at a as well as at b. If the function is continuous, function is differentiable, value at the endpoints are same. Okay, so the Rolle's theorem satisfied and there exists a point C in that interval AB such that the curve will have sharp turn at that point and the derivative tangent will be parallel to the x-axis. Tangent is parallel to x-axis. Similarly, in this case is also, in this case the function will have maximum value and in this case the function will have minimum value in that particular interval. Okay, so the f of x is differentiable on open interval ab, which means that the graph of f of x is a tangent at each point of ab. Now the existence of real number c such that f dash at c is equal to 0 shows that the tangent to the curve at x is equal to c has slope 0, that is tangent is parallel to x-axis. Just now I told you at this there exists a point at which that if you draw the tangent to the given curve, the tangent will be parallel to x-axis. This is the Rolle's theorem. Now let us see some of the solved examples based on this Rolle's theorem. Okay, The first example, we have to check whether the Rolle's theorem is satisfied for the given function or not. This is the function 2x cube minus 5x square plus 3x plus 2, and the interval is given that it's closed interval 0 to 3 by 2. Now as the first condition, it is given that the function is given. Now we have to check its differentiability and its continuity. Now if you see this function, it is a polynomial function, okay, and as it is a polynomial function, it is continuous everywhere, it is differentiable everywhere, okay. Polynomial function is continuous also and differentiable also everywhere. Now it is everywhere differentiable, so in particular this must be differentiable on the open interval 0 to 3 by 2, and it must be continuous on the closed interval 0 to 3 by 2. So our both the conditions are satisfied here. Now we have to look for the third condition, whether the value of the function at these end points are equal or not. So our a is 0 and b is 3 by 2. So we will put x is equal to a is equal to 0 in our function. So after putting the value, we get the value of the function as 2. So f of a is equal to 2. Now similarly we will find f of b. So put b is equal to 3 by 2 in a given function, and after simplifying we get 54 by 8 minus 45 by 4 plus 9 by 2 plus 2. So take their addition and subtraction, you get plus 2. So what we see here, f of a is equal to f of b. So value of the function at the end points are same. Hence all the three conditions are satisfied by this function. So hence Rolle's theorem is satisfied. Okay, Rolle's theorem is satisfied for this function. What they ask, we have to check only the conditions of the Rolle's theorem, whether they are satisfied for the function or not. Okay, so we have checked all the conditions and we conclude that all the three conditions are satisfied for this function. We don't have asked to find the value of c. Okay, again we have to check. This is the second example. Again, if you see, f of x is a polynomial function, okay, polynomial function, and polynomial function is continuous everywhere, differentiable everywhere. So in particular it is continuous on closed interval a 1 to 4 and differentiable on open interval 1 to 4. So first two conditions are satisfied. We have to think of the third condition. So value of the function at these end points, that is at x is equal to 1 and at x is equal to 4. So here a is 1 and b is 4. So find the value at x is equal to a is equal to 1. So 1 square minus 2 times 1 plus 3 is equal to 2. Now put b is equal to 4 in the same function. 4 square minus 2 times 4 plus 3, that is equal to 11. So here the value of the function at the end points are different. F of a is not equal to f of b. That means f of 1 is not equal to f of 4. Hence the third condition fails. So we say that the function, given function, does not satisfy the Rolle's theorem. Now, does not satisfy the Rolle's theorem, what does it mean? It means there doesn't exist any tangent which will parallel to the x-axis in the given interval. That is the meaning of Rolle's theorem is not satisfied. This is the second example. Again, the example given is a polynomial function. Again, we will write it is as it is a polynomial function. It is continuous everywhere, differentiable everywhere. So in particular, it is continuous on closed interval 0 to 4 and differentiable on open interval 0 to 4. Then we will go for the end points at x is equal to 0 and x is equal to 4. We will find the value at the end points. So f of a is equal to f of 0 and we get it as 10. Similarly, we will put b is equal to 4 in this given function. Then again we get 10. So here f of a is equal to f of b. So value at the end points of the function are same. Okay. So all the conditions of the Rolle's theorem are satisfied. So there exists a point C which belongs to the open interval 0 to 4. That C lies in the interval 0 to 4. And what is the speciality of this point C? The derivative of the function at C is equal to 0. So let us find the derivative of this function. Its derivative f dash of x is equal to 2x minus 4, that is 2 times x minus 2. So we will put x is equal to c in this derivative. Now f dash of c is equal to 0, which implies 2 times c minus 2 is equal to 0. It means c is equal to 2. If you see, this 2 lies in 0 to 4. C belongs to the open interval 0 to 4. So the Rolle's theorem is verified. Rolle's theorem satisfied is one concept and Rolle's theorem verified is another concept. In first case, we have just checked the three conditions of the Rolle's theorem, whether they are satisfied or not. Here in this case, we actually satisfy whether we have checked whether the Rolle's theorem is satisfied or not. And after the Rolle's theorem is satisfied, we have find the value of C also. So we have claimed the existence, we have shown the existence of C in the given interval. So Rolle's theorem is verified. Now the next example is given an interval AB, we don't know A, we don't know B, that satisfies hypothesis of the Rolle's theorem for this function. Means they are saying that for this closed interval AB, where A is given that A is equal to 0, but B we don't know. And they are saying that the Rolle's theorem is satisfied for this function. We have to find the value of B. Now how to find? Rolle's theorem is satisfied. So the three conditions are satisfied. What are those three conditions? The function is continuous on closed interval, function is differentiable on the open interval, and f of a is equal to f of b. It is also given. Okay. Now this f of x is equal to x cube minus 2x square plus 3. Okay. So we can simplify this function, this x cube minus 2x square. Okay, we call this as g of x. Then g of x is x cube minus 2x square, that is x square into x minus 2. So what is f of x then? G of x plus 3. Now we see that g of x becomes 0. Now this g of x becomes 0 for x is equal to 0 and x is equal to 2. So we observe that x is equal to 0, f of 0 is equal to g of 0 plus 3 is equal to 3. And for x is equal to 2, f of 2 is equal to g of 2 plus 3 is equal to 3. So at both these points, at x is equal to 0 and x is equal to 2, f of 0 is equal to f of 2. So obviously the function f of x is everywhere continuous and differentiable as it is a cubic polynomial. So consequently it satisfies all the three conditions of the Rolle's theorem on the interval 0 to 2. So we must have b is equal to 2. Okay, we must have b is equal to 2. Now this is the fourth example. Verify Rolle's theorem for the function. This is the given function and we have to verify the Rolle's theorem. Verify. Okay, take f of x is the given function. So now here e raised to x is continuous differentiable everywhere. Okay, You must know the graph of this e raised to x. Suppose this is our x-axis and y-axis, then graph of this e raised to x is like this. This is e raised to x. Here x is greater than 0. Okay, and the another graph is also there like this. Okay, this is e raised to minus x, and the point where it intersects the y-axis is 1. So these are the graphs of the function. So they don't have any break. So e raised to x is continuous everywhere. We can differentiate it. So it is differentiable everywhere. Now look at the sin x. Again, we know that the sine function. Okay, the graph of the sine function. How it look like? Sine 0 is 0. So it look like this. To the left of origin also the same. This is the sine rule. Again, sine wave. Again, we must know the graph of the cos also. Cos 0 is 1, so the graph will start from this point. To the left, again the same, just like a wave. And if you look at these three graphs, they don't have any break. Also, they are differentiable everywhere. So we use that property here, and then e raised to x, sin x and cos x, all the three functions are continuous and differentiable on their domains. Okay, so their combination, their composition must be continuous and differentiable everywhere. Okay, so therefore f of x is continuous and differentiable on pi by 4 to 5 pi by 4 and pi by 4 to 5 pi by 4 respectively. Okay, so now a is equal to pi by 4 and b is equal to 5 pi by 4. So a is equal to pi by 4. From 1 we get f of a is equal to f of pi by 4 is 0, and for x is equal to b, f of pi by 4 is also equal to 0. So f of a is equal to f of b. So the value is satisfied at the end points of the given function. So there exists c in this interval pi by 4 to 5 pi by 4. Okay, so the f dash of c must be equal to 0 for that particular c. Now what is the derivative of this function? We have to find the derivative. Now there we have to use the product rule. E raised to a first function as it is, derivative of the second function, plus second function as it is, derivative of the first function. So after finding the derivative, we get 2 e raised to x sine x. Now it is clear that f dash at c is 0. That means 2 e raised to c sine c is 0. Now e raised to c is never 0. I shown you graph of e raised to x, and it never intersect the x-axis. Okay, so the value is not equal to 0. So this sin c must be equal to 0. Now sin c is equal to 0 implies c must be equal to 0 plus minus 2 pi plus minus pi plus minus 3 pi plus minus 4 pi and so on, because sin c is 0 when angle is integral multiple of pi. This is the solution set. Okay, but out of which we must have the point which lies in this interval. So which is lies in that interval? Pi. Only pi lies in that interval. So c is equal to pi is the solution, and thus the Rolle's theorem is verified. Okay, so we will stop here. In next lecture we will see Lagrange's mean value theorem. It is also called as LMVT theorem.